Yeah, thanks first of all for the organizers for organizing this nice conference and for inviting me. So I'm a postdoc at the Humboldt University in the Integrated Photonics group. So we are an applied physics group, but I'm part of a small theory team which I supervise. And yeah, this is just my person. And I'm going to be talking about the spin-photon entanglement for color centers in diamond. So we already had a little bit of the, or quite a bit of the quantum dot perspective on how to create entangled photon pairs. And I'm going to provide the defect center in diamond perspective. So first of all, we already had a lot of motivation. So what can this type of entanglement be useful for? So for example, for quantum repeater chains, so you have Alice and Bob and some node in the middle that contains memory spins, and then spin-photon entanglement can serve as an intermediary that helps entangle Alice with the node and Bob with the node. And there's some details which I'm not going to talk about here much, but it is a very useful resource for sort of facilitating such a repeater. Then there are also there's an idea of a one-way repeater, so where you use a much more complicated photonic resource state, here the so-called tree cluster state. I'm also not going to go into a lot of detail on how you create the state, or yeah, I'm just going to say that now photons are represented by these dots, and entanglement is sort of indicated by the lines between them, and you can use a spin-photon interface to create such resources. And if you have access to a resource, you can compensate photon losses with such states. And yeah, but the key ingredient to realize something like this is again a spin-photon entanglement. Another very famous application that people in quantum computing community seek after, where also photons and large entangled photonic resource states play an enormous role, which is so-called measurement-based quantum computing. And here you can now, with the spin-photon interface, let's say, can prepare such a resource state where you have a lot of flying qubits that fly to your measurement detection apparatus, and you on the fly create this entangled resource again with some sort of spin-photon interface, and then measure it out, and in this way realize a quantum computing scheme. So there's a lot of like interesting directions and yeah, applications that such spin-photon entanglement sources can be used for. Okay, so the online audience missed the applications. Just showed a couple of images. The more interesting part comes now. So, so I will keep this initially quite didactic. So first, yeah, very quick introduction to color centers of diamond for the non-experts. So this is a group 4 color center. Group 4 meaning group 4 elements in the periodic table. So this can be silicon, germanium, tin, or lead, for example. And these atoms sit at an interstitial site between two vacancies in the diamond lattice. And then in the presence of a magnetic field or without, they have a sort of atomic level structure. And this atomic level structure gives us optical transitions. So first of all, there's 4 states in the ground state manifold. So initial degeneracy is lifted by the presence of a magnetic field. This magnetic field is needed to give you access to a spin qubit, which is the 2 states in the lower lying orbital branch here. So just the 2 lowest lying ground states. Then there are 4 excited states, and these, depending on the vacancy, can be split between 520 and 720 nanometers. So this, in a nutshell, is is what you need to understand the fundamentals of how the spin-photon interface works. And when I talk about spin, I always the interesting component here is are the 2 lowest lying ground states. So for this optical first entangling scheme that I'm going to present, the really important levels to understand the principle here is the standard scheme formed by the lowest lying excited state and the two ground states. This will facilitate one of the spin-photon entanglement schemes. So another ingredient that is really important that I haven't mentioned yet is a cavity that enhances one of the transitions. So this is through Bosell enhancement, and some of you might not be familiar with these types of cavities. So this is a design that was created in our group. So Julian Bock is one of the PhDs in our group. He worked really hard in optimizing this type of design. And for those who are familiar with photonic crystal cavities, that have a hole-based design where you create two mirrors, and then you create a defect, and this creates a cavity that locally enhances the density of modes. This is sort of similar, but now you don't have holes, but a corrugated external periodic modulation of your refractive index. And what this external corrugation allows you is really create a really efficient adiabatic section region here to couple photons very efficiently into a waveguide and subsequently into a fiber. So, but for this principal explanation, all that you need to know is that the structure will cell enhance one of the optical transitions. So in somewhere in there, there's our color center. And if you now want to create spin-photon entanglement in a so-called emission scheme, the first thing you have to do is you somehow to initialize this group 4 color center in the lowest lying ground state. And since you haven't created any photons yet, the photonic modes are in their respective vacuum state. So here are again the 3 states that I mentioned earlier. And the first part of this protocol is a preparation. So pi over 2 rotation, or it's not quite a Hadamard gate, but the result from this, starting from this initial state, would be the same. So you create an equal superposition. So here I keep track of the states. I present this now with an optical scheme of preparing the superposition, but in principle you could also do this with microwaves. And I talk a little bit more about this later. So then you do a state selective excitation. So you can think of a resonant laser that you shine on the vacancy to prepare this excited state. So here you have track of this, and this is followed by a spontaneous emission event. Here's where the Bosell enhancement becomes important, because in principle other transitions are allowed, which would reduce the efficiency of the scheme. Then you do another pi flip and another state selective excitation, and voila, the resulting state that you prepared in this way is a spin-photon entangled state, where your spin is now entangled with a time-link qubit. So you can also repeat this, and depending on the, if you identically repeat these steps, you create a so-called linear cluster state. You leave out one of these rotations, and you create a big GHZ state. And these sort of are preliminaries to more complicated entangled states. And this has already been achieved with quantum dots and atomic sources in these really seminal works quite recently. But so far it has not been done with color centers. So so this is an emission-based scheme. There's another idea which has already been implemented, which is called reflection-based scheme. So now I show a very simplified setup. So there are photons coming into this circuit here. We have an internal source that I'm not going to explain what it does in this. I only want to talk about the entanglement, the reflection part. Again, you have some kind of adiabatic coupling to a cavity that you can control with either microwaves or optically. And then there's a measurement unit that you can use to either analyze your entanglement, or you can just route your reflected photons into a network. So these are the ingredients. Again, let's say you can prepare such an initial state. Remember, the goal is spin-photon entanglement. Your memory is initially prepared in spin down. Then you again prepare an equal superposition, either with a microwave or optically, of your spin. This is your initial state. So the first thing that happens is that, so these are time intervals, right? So the first photon that will interact with the cavity will get reflected off it. Now the trick here is that this reflection is spin dependent. So this is from a paper where they showed that you can get an entanglement assisted boost in the rates, and silicon vacancy in diamond that acts as the memory, so not the tin vacancy, but the silicon vacancy. And the reflection, what you can see here now is that the reflection, the cavity reflectivity depends on the spin state. So this thing, the cavity becomes transparent, so photons will just fly through it. If the spin is in spin down, and it's reflective if the system is in spin up. Now what happens with the first photon? It's reflected. So since I prepared a superposition, now my reflective activity is also respecting that, and the first photon gets reflected, but only based conditional of this spin state. The second photon does the same, and I end up with this spin-photon entangled state again. But here I may ask now the audience if there's any sort of issue with this type of system, with this sort of scheme, if I base it off a cavity that's either transmissive or reflective. Does anyone have an idea what a fundamental issue you arrive if you do it this way? It's also sometimes called entanglement carving. It's also the idea comes also from hot atoms. So you will lose 50% of your photons that gets transmitted. So this is sort of inherently limited to 50% efficiency for creating this type of entanglement. Yeah, so here I just added a final step. If you read out your photon, so if you route it to this measurement unit, you can save a state in your memory. So there's another scheme that is based on a half-open cavity, and here I now just show, so it's more like the cavity I showed, and here I just show the real part of the reflectivity, and you can again see that depending on the spin state, so red is spin down, blue spin up, the real part can either be positive or negative here at this operation point. So that's, if I'm at zero detuning, the real part of the reflectivity will either be +1 for spin up or -1 for spin down. Now you can play very similar game. So let's say you have this time-bit qubit, and your system is just where it spin down, and you reflect it, and you do a pi/2 rotation of your memory, of your spin. The late photon gets reflected, but now you introduce this phase flip here in the second reflection due to the reflectivity. And remember, I only showed the real part, so the imaginary part will also be non-zero, so the total reflectivity will be 1. But this is the trick here is to exploit the phase that you introduce through the spin-dependent reflection. And voila, if you rotate the spin again, you end up with a spin-photon entangled. So now this can in principle have a much higher efficiency, so it can be larger than 50%, and you mainly limited by losses. So there are two aspects to this: the efficiency and the fidelity of the state that we create. And the efficiency is of course very important, and then the fidelity of the state that you can create can be affected, for example, by the bandwidth of your early and late photons. So since this is frequency dependent, if you had a very broadband photon, then the space wouldn't be like perfect entire frequency range of your photons. So this can produce a fidelity issue at this gate. So you have to either carefully engineer this cavity to match your photons, or play with the source photons to get good and high fidelity entanglement. Yeah, so you can also use this then with delay lines and switches to use, again, interesting large entangled states. So this is a nice proposal here from Xi. And so depending on how many delay lines and switches you have, you can use this reflectivity scheme to build up these larger entangled resource states. So however, these were just very idealized schemes that I showed. There are certain challenges which are always very hardware specific. So the quantum dots face many challenges, but the color centers are also troubled by some problems or issues that have to be overcome. And one of them is this control. So you can always write down these control sequences, but once you try to benchmark them or try to assess how well you can do them, you have to sort of take into account all the details, like the high excited states, and also there are many interactions that will screw with your microwave control. So you have to work a little bit harder and to figure out how well these can actually work. There's a sort of interesting story for group force color centers in particular, that microwave control either requires very highly strained emitters or special field configurations. This is something I worked on with Humboldt, one of the PhDs in our team, and Yannick is working on the optical control. But long story short, it's just, it's not that straightforward to just engineer these control operations that are required for all these schemes. And you kind of have to figure out how to make them work efficiently for these color centers. And optical gates at not such high fidelity as in experiments, and microwave control only has been shown recently to work for the tin vacancy. So for the silicon vacancy, this is quite well established, but since the tin vacancy has larger spin orbit coupling, and changes a little bit the way it interacts with strain, this has been much more difficult. Then there are the optical interfaces. So to make this highly performing, you need to have a very efficient design. So if you're limited by losses, then you have to work really hard. And one of the avenues that was picked in our group is to really make these adiabatic tapers and couplings to fibers work very efficiently. And there's the optical coherence, so meaning in part the indistinguishability of the photons. If you use this as an emission-based scheme for entanglement, and one of the big benefits of these group 4 vacancies is that they're less sensitive to electric noise. But it turns out that when they're implanted, they create a lot of damage in the lattice, and this creates vacancy complexes that can be charged. So, and these can also be very close to your defect. And if they are charged, you can get inhomogeneous broadening due to this electrical noise that will reduce inhomogeneous broaden your emission line, which will then reduce the indistinguishability, which will become an issue in the fidelity of all your entanglement generation schemes. And for group 4 vacancies, this is even wilder. So we measured really big jumps that we could temporarily resolve in the emission, where we could identify the individual vacancy complexes that were that were responsible for these jumps. So they're only recently, or in the last 2 years, the recipes for the creation of these vacancies has improved such that you can get really narrow and stable lines for the tin vacancy. So these are all really big. Idealized schemes, seemingly small things, but that you really work hard on to make this work for color synthesis. But yeah, there's lots of progress here, which is promising. So then I can just give you a quick, like one example here for optical control, how the specifics of the system can affect an idea for control. So I mentioned that in my overview that I'd like to use Raman, or that I presented it with a Raman scheme. So you have like two laser pulses that are somewhat detuned from the lowest lying excited state that have two different carrier frequencies. So this couples to your vacancy, which is described by some Hamiltonian H naught through the electric dipole interaction. So here are your two pulses. They can have, in principle, two different amplitudes, but for the sake of this example, they have the same shape. Only, so it's Gaussian pulse, same shape, two different carrier frequencies. And now, if I don't include any losses, just look at the coherent evolution, and I want to make a pi gate. I let these interact with my vacancy, and I get like a perfect population inversion. So this is everything is perfect. I get the outcome that I need for my pi gate, and then I look at the sort of transient population in my higher lying excited states, and I see like a little bit of population. Couldn't be that bad, right? But then if I introduce phononic, so the vacancy, since it's coupled to a lattice, there will be it will also couple to small distortions. So these will introduce decay channels in my excited, and also actually in my ground state manifold. So these are incoherent processes, and this little bit of transient population will completely kill the fidelity of this operation. So you sort of have to take these into account and then optimize your gate, having these in the model, and then you can also play with a lot of these other like external classical control parameters, the direction of your magnetic field, and its magnitude and pulse durations, and so on and so forth. And of course, if you have some Purcell enhancement, then you also have to keep that as part of your model. So this will enhance one of these transitions, and this all will affect the fidelity of your final gate operation. But it turns out that you can get quite good fidelities for this optical scheme once you optimize all these parameters. So a little bit above 99%. So these are just parameters that go in here, and then you can look at how this fidelity is affected by, for example, increasing your Purcell enhancement, and in general it will get worse because during a pulse, if you enhance one of the transitions, there's a greater probability of decaying during the pulse, which creates two photon excitation events, and this will then affect the fidelity of your resulting states. So there's like a sort of sweet spot for your cavity, for an ideal cavity parameter. Don't want to have infinite Purcell enhancement. And you can take this into account and look, for example, benchmark then your protocol with the creation of these larger entangled states. So here I'm showing the fidelity of a linear cluster state as a function of the number of photons. And then this can also very much depend on the magnetic field strength. So here in this particular example, it performs okay for very large fields, and this is not yet ideal because we can't really create these strong fields in a cryostat easily. But it sort of shows you what kind of games you can play if you have a model that takes into account all these effects. Yeah, with that, I come to my conclusion. So this is particularly for the generation of cluster states, but for all these entanglement schemes, you need to do a quite extensive optimization of your parameters to really find a regime where they work well. And if you go this all optical direction, if you want to stay within the coherence time, then maybe doing this quickly, yeah, we didn't really talk about the speed aspect here, but doing it quickly can become really important. And that I want to thank you for your attention.
Any question? I mean, as you mentioned, let's say the emission scheme has been realized by using atom and also quantum dots. So, in my naive understanding, quantum dots is more nasty than your color center here. So why the color center has not been realized? I mean, what's the main challenge here? I didn't get it.
So historically, I think people don't work as hard towards it because the quantum dot is such an excellent single photon source already. So it's like going the next step, which is the creation of these larger entangled states. So people are not really putting all their effort into just the single photon generation. But it's of course, if you go down this emission route, I think there will be similar challenges that the quantum dot community faces. Like when you take full account of the pulse and sort of the dissipative mechanisms in the excited states and how it gets affected by the pulse itself, there will I think I can see how it can become also quite nasty.
Okay, that means you prefer more this reflection scheme in your case.
Yeah, so also because it has been already implemented by the Open Group and has been part of one of the works that you've shown. So I think that these reflection-based gates, I think, are much more promising.
Could you go back to the slide of you had when you construct the GHD state? I know Dr. Gregor mentioned. There we go. So all those states or losses, right? Has this been actually experimentally demonstrated that this works for large enough GHD states? I know that IBM was able to make them, I think, up to like 18 or 20 was a fairly reasonable fidelity, but they're using the superconducting qubit architecture. I'm curious as to what happens here.
So I think in the first reference it was maybe 14 qubits of the GHZ, if I remember correctly. So, but this is with atoms, and with color centers this has not been done yet. This was something we were working on. But indeed, so the efficiency of doing this is very much affected by all the losses. We estimate, I think, Hertz rates for 100 photons. So 1 per second, but maybe if you use, if you can detect undesired emission events, you can sort of abort your protocol after when it happened, and maybe this can increase the rates of the generation. The rates are not very high due to all the losses and undesired emissions that can occur.
And those losses, they're basically fundamental. You cannot get rid of them unless you somehow change the material in which you are propagating these photons. I mean, it's kind of, they're small, but they're fundamental. They're always going to be there. So at least in superconducting, you can hope that by isolating the system well enough, you get rid of the pathway to do this. I mean, I think that this might still allow you to get very large GHD state. It's just there's going to be a fundamental limit, and it would be nice to somebody study that as well.
So we looked at it so can assume all these coupling losses, all the internal losses, and so on and so forth. And we looked a little bit into it for fiber losses. So your state will have some extent. So first photon emitted will have traveled and then quite a bit, so will be affected by loss and then sort of multiplies for all the other subsequently emitted ones. So there we saw that it gets like, it gets really bad after 100 photons a year.
Thank you.